All right, I guess we can get started. All right, welcome to week 9 of AI612. This week we'll be covering medical text. So today we'll be covering medical text, and then on Thursday we'll be announcing the second project, medical text, which will be based on medical text, and actually the task itself, which will be automatic coding, that will be covered today. So the task itself and the representative example or representative model for doing automatic coding will be described today. Actually, let me just mute everybody. All right. Yes, okay, so as I was saying, the representative model for doing automatic coding will be described today, but the specific specs will be discussed this Thursday. And as I said, if you guys are interested, some of you who have acquired a decent amount of score, decent enough amount of score for project number 1, you can propose to do your own project until the end of the semester. So you don't have to do like project 2 or 3, which will be, so project 2 will be medical text. Project 3 will be based on medical images. So project 3 will be classifying images into specific diagnosis codes. Today, this project number 2 will be classifying medical text to specific disease codes or diagnosis codes. So the 2 will not too much difficult. There will be some amount of pre-processing, like project number 1, but it won't be as unfamiliar as project number 1 because you've already done it. So hopefully you guys are familiar with the structure of mimic 3, and project 2 will come more naturally. Project 3 will not be based on mimic 3. It will be based on mimic CXR, which is a different data set. So that's a different story. But project number 2 will be based on mimic 3, and hopefully you guys can have an easier time doing project number 2. And as I said, if you guys have like a interesting project on your mind, then you can discuss that with me. So the specifics will be covered this Thursday. So today we'll be covering medical text. Hopefully, there isn't that much material, so hopefully we can finish within maybe hour 20 minutes, 10 minutes. All right. So recap. So last week we talked about the graph itself, the graphs and the graphical knowledge or external knowledge in biomedical field and how to view EHR as a graph. So domain knowledge we saw how to inject or incorporate DAG structured domain knowledge into the model along with the EHR. So EHR is an information from the hospital, how they operated, how they treated patients over a long period of time. But on top of that, we use external knowledge source, such as diagnosis code hierarchy, or as an example, I showed you guys SNOMED CT ontology. And the second part, on last Thursday, we talked about how to use the internal knowledge, which is the EHR itself, how to view EHR as a graph, and how to use the graphical structure of EHR, or how to learn graphical structure of EHR. So using graphical structure of EHR was rather straightforward. You can think of just simply applying graph convolutional neural network on EHR dataset if you already know the structure of EHR. And if you don't know, or if you don't happen to know the exact structure, or maybe you just know partial structure of the graph, then you can combine graph neural networks with transformer, which are actually the same thing. So you can combine the two. You can build a hybrid model, and then hopefully with enough amount of data and regularization, transformer can learn useful attention network or attention strength that is similar, that resembles the true ground structure of the graph. So that was last week. So this week, or today's focus, actually, today's focus is medical text, and there are a lot of medical text, but we'll just be looking at text in mimic 3 in more detail. And then we'll be looking at 2 representative examples in modeling clinical text, which is using one-dimensional CNN. I mean, obviously you can use recurrent neural networks to encode or embed medical text and then do some classification, but the first example of using neural networks for automatic coding was actually based on one-dimensional convolutional neural network. So we'll be looking at that. And then the second representative example is BERT for biomedical text. There is, of course, there is BERT, and there's like Albert, Roberta, there's Electra, a lot of like BERT variants. But then there is another subgroup of BERTs that is used for, or that is trained for biomedical purposes only. So we'll be looking at that. Right, so far we've only dealt with, actually this is a typo. Right, so far we've only dealt with structured information. If you think about what we've learned so far, before the first project, what we learned is just how to build predictive model based on EHR, and the code, the information or the features that we've used in the example, or actually in project number 1, was all structured codes. So it was either demographic, so demographic meaning 신상 정보, or 인구 정보, so demographic. So that the examples could be ethnicity, gender, or the age, marital status, that kind of stuff. So those were usually on stored in the patient's table or the admissions table. So those are all, so as I said, those are stored in tables. So table is a tabular structure. So anything that is stored in a table could be seen as a structured information. Admissions, so what we've used is also admissions related information, such as admit time, discharge time, primary diagnosis, admission type. Those were like categorical values or numerical values, something like that. Diagnosis codes or prescription codes, those were also codes. So information related to diagnosis itself. So information related to diagnosis or codes. So do not be confused with diagnosis and diagnosis code. Diagnosis is an action. It's 진단 행위가 diagnosis고요. And so diagnosis is an action, and a code is the result of actually doing the diagnosis. So diagnosis code is what is left after the action. So code, and maybe you could also, if you've looked up the Make3 dataset enough, then you will know that there is a dictionary table like D ICD-9, a D diagnosis ICD. No, was it D underscore ICD underscore diagnosis? So code and descriptions, and maybe sequence numbers and that kind of stuff. Prescription had a bit more information. Prescription had code again, so the medication code or medication description was there, and then the amount of the medication, start date, end date, routes, and that kind of stuff. So those were all in tables. So that's why we call them structured information. And those were relatively easy to use as features. If the information that we're using were numeric values, then you can just simply use them. You can just plug them into the neural network, or you can normalize them, using minus the mu divided by the sigma. You can like z normalize them, whatever, if you want to, or you can just quantize them into different buckets and then use them as values. That is up to you, but still, basically, numerical values can be still used like relatively easily. Categorical values, you can use them as one-hot vectors, so on and so forth. So they would take up a lot of space, because if you think about diagnosis code, if you think about using diagnosis codes as features, then there were about 14,000 different diagnosis codes. So you would need to prepare 14,000 dimensional vector at least to use diagnosis codes only as a feature. So that would take up a lot of space, but still it is relatively easy. And that is what you did with project number 1. Compared to that, medical text is actually what we call unstructured information, but that is not the only unstructured information. Medical text, along with text images, are also unstructured information. EKG signals, 심전도 검사들, those are also signals. So those are time series, like wave-like data, like it's like audio recordings or speech recordings. So images, EKG signals, of course, speech recordings, like when doctors and patients, they talk about the symptoms, or doctors consult the patients. Usually, sometimes they are recorded in the recording device, and then they are actually released on the web as like a training set. So those are also unstructured information. So text, images, signals, there are actually a lot of unstructured information related to clinical practice or medical in the medical field, but text is one of the most prevalent unstructured information. So if you think about it, if you think about the number of times each information occurs, then you could probably guess which one is the most prevalent one, which is of course text. So images, like you don't always take X-ray images, or you don't always take CT scans or MRI scans. And similarly, you don't always take EKG or EEG, which is 뇌파. You don't always take EEG. Like every time, you don't take those kind of labs or tests or special kind of processes whenever you go to the hospital. But text is usually there. Is usually whenever you go to the hospital, text is always it is always recorded in some manner, like as a admission notes or discharge summaries or physician's notes or whatever. And text is where also, before we get into this, so text is everywhere. So text is, we don't talk about just clinical notes, not the ones that are in Mimicry. We're not talking about those texts only. We're talking about text that is related to medical field, like in general. So for example, like textbook used in medical schools, 교과서죠, 의학 교과서. So textbook is also very important information. Everything that is used by practice by the physicians, those are from text-based information, because they read a lot of textbooks and then they actually memorize a lot of information. So I'm not sure if any machine learning models were trained on medical textbooks yet. Maybe Watson from IBM. So Watson is if you're familiar with Watson, so it's it was a project from IBM, and it was, so what the original Watson, what it did was actually was a machine learning model for solving trivia questions. So so Watson was actually the model that participated in a quiz show called Jeopardy. 제퍼디라는 미국 그 퀴즈 쇼가 있는데 거기에 이제 출전을 했어요. 왓슨이라는 그 머신러닝 모델이. 그래서 사람을 상대로 이겼습니다. 이제 그 제퍼디에 가장 그 우승을 많이 한 사람이랑, 그다음 제퍼디에서 가장 상금을 많이 딴 사람이랑 이제 둘이 나오고, 그다음 기계가 나와서 이제 그 퀴즈를 풀었는데 그때 왓슨이 이겼어요. 그게 so that was back in 2013, I think, or 2012 or 2013. So that's quite a long time ago, actually. That was all before the deep learning era began. So actually, the Watson, what Watson used was mostly based on classical models, like information retrieval, support vector machines, classical, like pre-deep learning models. And even with that, even with that classical approaches, just with a very intricate combination of a lot of techniques, Watson was able, like IBM was able to beat human participants in Jeopardy. 제퍼디 장학 퀴즈 같은 쇼라고 말씀드렸죠. 문제가 나오면 그걸 이제 딱 듣고 3초 안에 뭐 풀고 뭐 그런 겁니다. 네. So that was back in 2012, and then so that was a pretty big hit. It was like GPT-3 of the day, GPT-3, or what's popular these days, or AlphaGo challenge. So AlphaGo challenge was 2016. So that was also, so AlphaGo challenge it took place in Korea, and obviously Watson Jeopardy challenge took place in the United States, obviously. But still, it was a pretty big sensation back in the day. So I was actually working as a researcher in ETRI, 한국전자통신연구원에서 병역 특례를 하고 있었을 때인데, 그때 이제 아주 히트가 나가지고 이제 그 큰 국가적 과제가 생성이 됐습니다. 이제 왓슨 같은 걸 따라하는 한국형 K 왓슨을 만드는 한국 과제가 막 만들어지고 뭐 그랬었습니다. So Watson, after the celebration of Watson beating human participants, then IBM decided to use that for biomedical purposes. So Watson, the original Watson, was trained on a lot of like general knowledge, because Jeopardy is a general knowledge question answering framework. So it just went through a lot of like Wikipedia, probably like a lot of like books and stuff. But when IBM decided to use or retrain Watson as to serve as a biomedical clinical decision support system, like to make them behave like doctors, basically. So I think it was called Dr. Watson or something. They retrained, or they trained Watson on a lot of medical knowledge. So a lot of like medical journal abstracts and a whole bunch of structured clinical knowledge and stuff. And I think I read from somewhere that Dr. Watson was also trained, or not exactly trained, because what Watson does is not actually embedding text, because this is all pre-deep learning era. So they just they go through a lot of text, and then they extract structured information from them, like subject, object, and predicate. 그러니까 주어, 서술어, 목적어, 이 트리플이라고 하죠. 이제 SPO라고 그러는데, 이 SPO를 이제 뽑는 겁니다, 이 텍스트로부터. 그래서 they extract these triples from like massive amount of text, and then store them in some form of database. And then when a query is entered, they parse the query and then look up the database to look for relevant triples, and then somehow they do like inference and that kind of stuff. So I think Dr. Watson went through a lot of medical textbook and then extracted a lot of triples, and then stored those triples in its internal database. So I'm not sure if any recent deep learning models go through the medical textbook anymore, but they can if they want to. So we'll talk about that in BERT variants. So textbook used in medical schools can be a good source of medical information or clinical knowledge. Biomedical journals, these are also like very old source of knowledge, especially for NLP people. So biomedical journals. So usually when I say biomedical journal, I'm talking about PubMed abstracts. So PubMed is a repository for all biomedical journals. So like whenever you submit journals or papers in biomedical journals, like bioinformatics or journal of medical information research, so something like or whatever, like Cell or Nature, nucleic acid research, whatever. Any biomedical papers you submit, you will be submitting it to some journal, and then those are all compiled in PubMed. So you can look them up. PubMed is basically a search engine for all biomedical papers. And there is a data set called PubMed Abstracts and PMC, which is PubMed Central. So there is a data set which is like a dump of bunch of medical journal, a bunch of biomedical journals from PubMed. So you can use them to train your models or build a search engine or whatever you can do with it, whatever you want. And before the deep learning era, a lot of people actually use those PubMed journals or PubMed abstracts to extract structured information. Again, extract structured information such as like which gene incites which activation, like which gene generates which protein, or which protein actually inhibits the activity of which genes, or which genes are correlated to which other genes. Like those are all like subject object predicate. So you can try to extract a lot of triples, like biomedical related triples from those journal abstracts, and then build an ontology, build a knowledge graph. So like in those knowledge graph, like entities or nodes will be genes, and then the relations would be like inhibits or correlated with or activates, some kind, like that kind of stuff. So that was all like back in 2000, like even before 2010. So those are all for like really classical tasks that are still actually ongoing. It's just that the tasks are there. The approaches or the techniques are now all like recent deep learning based. Text crawl from the web can also be a good source of knowledge, like Naver 지식인, so Naver Q&A. There is a lot of medical related questions and answers in Naver 지식인. Similar things were also there in the United States website is called WebMD. So there's a website called webmd.com, which used to be a community where you ask questions related to like health. So it's basically a healthcare community. So you could ask like your symptoms and then the community users in there would give you like tips or answers or recommendations. Like, you could ask like, I have rashes in my arms. What do you think they are? And then another user could answer like, oh, those seems to that is usually due to what, yada yada yada, some blah blah blah. And then you should look for like some doctor, like dermatology doctor or whatever doctor, or you should take some you should eat something. Like basically it's a community-based recommendation or question answer website. It used to be, but when I actually visited WebMD like a couple days ago to see what happened to the website, it became like a total clinical / healthcare portal, like Yahoo of the day or Naver recent. Like it's no longer a community, it's like a portal with a lot of advertisements. So it became like a total package of all healthcare related news, articles, blogs, recommendations, like dictionary definitions. And I could no longer find the community, like the community boards. I don't know where they are, but it used to be like the go-to sites for like average non-clinical people. So again, yeah, text scroll from the web could be a good source of information. And obviously notes from hospital are probably the most clinical. So healthcare and clinical and biomedical, those are like slightly, there is some subtle nuanced difference between those terms, but clinical is usually 의료행위 or 임상. So it is, when you say clinical, it means that something that is happening in the hospital when treating patients. So notes from hospital would probably be the most clinical knowledge containing source of information out of all these text, all these different types of text. So in the notes from hospital, there are like discharge summaries, radiology reports, nursing notes, like yada yada yada. There is a lot of different kinds of hospital notes or clinical notes. So we will be looking at some of the examples. So we'll be looking. So what we're talking about is actually text in Mimic 3. So all free text is stored in note events table. So this is the only table in Mimic 3 that contains free form text. So all the other tables are actually just structured information, like medications, labs or demographics, diagnoses, admissions, ICU stays, whatever. So note events table contains about 2 million rows. So that's a lot of rows, and it is about 3.7 gigabytes of data. So this is the second largest table in Mimic 3, and you would probably know which one is the the largest one, which was chart events. So that was about 33 gigs of data. So second largest is note events. So text is actually a big information, as I said, and it is fully anonymized. So if you look at the example here, it is still a table. So there is columns and rows. So the columns are, as you can see here, row ID, subject ID, hospital admission ID, chart days, chart time, store time. So these are probably, you guys are all familiar by now. The category is the category of the notes. So there are like, radiology report, nursing notes, discharge summary. Those are like categories. And the descriptions are actually the lower level descriptions. So like under the category, there's different types of notes. So those types are described in this description column. And then the final column is the text itself. So you can see that row ID like 174, subject ID 22531 hospital admission ID is 167853. Dates are here. Category is discharge summary, and the description is report. And then then there are some blank information which are CGID and is error. So you can text starting from here, admission date is where text begins. So the text column begins here. So admission date, then there is a bracket and some asterisks, Then there's discharge date, brackets and asterisks, and then there's like what kind. So this is a discharge summary. 그러니까 퇴원 보고서라고 볼 수 있겠죠. 이제 사람이 환자가 입원에 퇴원할 때 이제 이 사람이 그 입원하는 동안 또 ICU에 들어간 동안 무슨 일을 겪었는지를 이제 쫙 이렇게 글로 대략 이제 카테고리별로 뭐 서비스는 뭘 받았다, 그 영상은 뭘 찍었다. 근데 그 중에 헤드 CT는 헤드 CT에는 뭐 뇌 안에 그 출혈은 없었던 걸로 보였다. 그다음에 그 복부 CT도 복부 CT 봤는데 티탄 어딘가에 뭐 문제가 있었던 걸로 보인다. 그다음에 또 뭐 쭉 있습니다. So it's a summary of every single thing that the patient went through during the hospital stay. So you can see that there's different sections in the discharge summary. There's service section, there's radiology study section, head CT, abdominal CT, abdominal CT, and then there's obviously like prescriptions section, there's the diagnosis section, procedure section. You'll be familiar. You can look at it by yourself. You've already downloaded notes events in your local hard drive. But what I'm trying to show is that there is a special looking brackets of asterisks here and here, again here, and those are all private information. So that is why they're actually anonymized. So like year is all translated to the future, like 2151 July 16th. This is like in the future. So like these are all anonymized. Names are anonymized. Like there's like name 8, name 4, last name. I think this is the doctor's name. So this is the physician's name. So first name, middle name, and last name, and then the license number, or like the MD number or employee number, and then there's hospital number. There's job number. I'm not sure what job number is. Again, but there's also still like different like dates. So like anything like patient names, physician names, phone numbers, exact dates, locations, address, hospital related information. Those are all like, private information that shouldn't be exposed. So those are all fully anonymized. So anything that starts with a bracket and a like square bracket and 2 asterisks, they are actually, you can think of them as anonymized information. So when you try to embed or encode or process these clinical texts, you can think of how to deal with them. If anything that starts and ends with a square bracket and asterisk, you can either throw them out or you can just encode them with a special token or whatever. All right. So as I said, there are 15 categories. So there are discharge summary, there's echo, which is echocardiogram, 그 초음파 진단, 이거 초음파 보고서죠. 초음파 뭐 복부 초음파를 한다던가 심장 초음파를 한다던가 그러면 이제 그거에 대한 또 어떤 진단서나 소견서가 딸려오니까 이제 그 관련된 게 이제 echo죠. So echocardiogram is actually like 초음파, supersonic. Yeah, actually, echocardiogram is for your heart. So I'm not sure how 복부 초음파는 영어로 뭔지 모르겠네. So anyway, so anything that is related to like 초음파 is all echo. ECG is electrocardiogram, which is 심전도. Nursing notes and physician notes. These are like daily things. Like nursing notes, they are recorded or they are written every single, like maybe every 8 hours or every 16 hours, 24 hours, like, nurses would. So when you're in the hospital, when you're admitted, so 입원을 하셨을 때 또는 특히 중환자실에 들어가서 누워 있을 때, 그때 이제 뭐 몇 시간 간격으로 이 간호사분들이 와가지고 체크를 하잖아요. 뭐 불편하신 데 없으세요? 뭔 어떠세요? 뭐 체크하고 뭐 혈압계가 잘 껴 있는지, 뭐 소변줄이 뭐 잘 붙어 있는지, 뭐 이렇게 계속 체크하잖아요. 그런 거를 담아두는 게 nursing note입니다. So nursing notes is generated every 4 hours, 8 hours, by some period when you're in the hospital, when you're admitted, and when you're in the admission ward, or when you're in the ICU. So they check up on you. So like whether if you are experiencing any uncomfortableness, or if your like devices are all like properly hooked up to you, whatever, something like that. So that is why nursing notes are the most, the largest number of there is like the amount, the most prevalent source of information. There's about, out of all the like all the 2 million rows, there are about 800,000 of them are nursing notes. Physician notes are not as frequent as nursing notes because doctors actually usually check up on you like every single day, like once per day, or maybe once per 2 days, like bi-daily basically. Rehab services, case management, these are like some other kinds of services. Respiratory, like if you are hooked up to some ventilation system, 그러니까 이제 호흡기 관련된 걸 뭐 끼고 있으면 이제 그런 거 뭐 하는 것 같고요. Nutrition, general, social work 이제 그 사회봉사 활동하는 뭐 그런 분들이 오셔서 뭐 하는 뭐 그런 거겠죠. Pharmacy, consult, radiology, nursing. So there are 15 categories, and distribution of notes over categories look like this. So most frequent are, as I said, nursing notes, and the radiology is actually is the next frequent, the second frequent notes. So when you take CT scans or like X-rays or MRIs, whatever, and they're all there. And then nursing, another types of, so as I said, there are categories, and there's like there is description. So you can think of nursing other and nursing as the same source of information. So you can see actually they are over 1 million. There are over 1 million nursing related notes. The physician notes here, discharge summary. So this project number 2 will be actually based on discharge summary. So here, right here, it's about 50,000 notes, or somewhere between 50,000 or 60,000, which is way less than nursing notes and physician notes. So project number 2 will be based on discharge summary, as we will see today. So this is actually a category divided by 2 of the students in our lab who, when they actually went through a lot of notes to see what kind of information they contain, and then they came up with 5 different types of notes. So type 1 is discharge summary, type 2 is physician related notes, type 3 is nursing related notes, type 4 is radiology, echo, and ECG. You can think of probably why they're in the same category. They're after you take some tests like image related tests, like radiology is so radiology is actually called radiology because this is 방사선이잖아요. 이제 방사선과니까 엑스레이도 방사선을 쬐는 거고, CT도 엑스레이를 이제 이렇게 다른 축으로 이렇게 Z축 생성을 이렇게 쭉 훑으면서 가는 거거든요. 이렇게 몸통을 쭉 훑으면서 가는 거라서 그것도 X선이고, 에코는 사실 다시 잘못 말씀드릴게요. 레디올러지, 그 방사선과라 부르는 이유가 엑스레이도 방사선이고 CT도 엑스레이니까 방사선이고 MRI도 뭐 자기 공명 같은 거 해가지고 뭐 무슨 막 해서 뭐 하잖아요. 그러니까 이제 다 그런 게 다 방사선을 쬐는 거에 뭐 관련이 있으니 그런 걸 이제 방사선과라 불러가지고 이제 radiology image라고 합니다. So those are all radiology images. Echocardiogram, 이건 초음파니까 방사선이 아니죠. ECGs, these are electrocardiograms. So you put some sensors on your chest and your like arms and legs, and then you basically try to measure the electricity that is like dispersed, that is propagated throughout your body. So that is also not related to radiology. So but basically eventually they're all recorded in the form of images like JPEG images or DICOM images. So that's why they're all in type 4. Type 5 are like etc. So rehab services, case management, general, social work, pharmacy, consult. So those are not really those are related to like some supporting or auxiliary services done to the patient, rather than giving drugs or doing procedures or operations. These are all a bit more supporting roles. So there are five types, and so let's just take a look at each of the type, maybe in a quick, maybe briefly, because we still have a bit more to cover. So type 1 discharge summary. So these will be used in automatic coding. So maybe you can maybe we can spend some time here what they are. So type 1 discharge summary. So key features are all of them have a similar form. So as I said, there are sections in discharge summary, like service section, radiology section, prescription section, procedure section, diagnosis section. There are sections. So all of them have similar form, and mainly they contain personal information. So like the age of the patient, or like the symptoms of the patient, the like gender of the patient, they're actually in the free-form text. And then the historical information, like what the patient has gone through previously before this admission, like whether the patient has been smoking, whether the patient had some family like hereditary disease or genetic disease, or whether the patient had like a major surgery before this admission, something like that. So, and then hospital course information. So what the patient went through this time in this admission, this hospital stay. So all the physical examinations, results from the labs, hospital, like brief hospital, like basically what the patient went through in the different, like in the whole process. And then medications on discharge, admission and discharge, like what the patient was on, what kind of drug what patient was taking at the time of admission and at the time of discharge. And then what the patient's status was at the time of discharge, like if the patient was fully recovered, or whether the patient still need to come back to the hospital like regularly, or whether they are discharged to not to home, but to like care centers or nursing facilities. So if you're not fully healed, but you're good enough to be discharged from this hospital, then you would be going to like caretaker's home. 그러니까 뭐 요양원 이런 데 갈 수도 있잖아요. 이제 병원은 바쁘고 손님이 아니지, 병원도 어쨌든 새로운 아픈 사람들이 항상 생기니까 이제 어쨌든 자리를 빨리빨리 비켜줘야 되잖아요. 항상 뭐 계속 입원해 있을 수는 없으니까 그때 이제 대충 좋아지면은 이제 요양해주는 이제 nursing facility로 이제 뭐 discharge니까 뭐 퇴원시키기도 하죠. 네, 뭐 그런 겁니다. Discharge diagnosis is like at the time of discharge, what kind of diagnosis you received during this ICU stay or hospital stay. So like at the front, from the time of admission to the end of discharge, you probably went through a lot of stuff, and then diagnosis and prescriptions, medications are like they would be, a lot of codes will be recorded in discharge summary. And discharge instructions, like what to do at the time of discharge, like come back to the hospital regularly for like every week, or like do something, do that, like don't take shower, whatever, like some instructions would be there. So distribution of subcategory, this, what I mean by subcategory is actually the description set column. So category, we're talking about discharge summary category. And then under this discharge summary, there is description. There are two descriptions, which are report and addendum. So report is actually just the report itself, and addendum is what is added to the report after the report was generated. So the report is generated, and then it is stored in the database, which is note events. And then after some time, maybe the hospital workers, like nurses or doctors, would like to add some additional information to that, to the discharge summary. So they would write addendum. So you can think of addendum as just additional information. So yeah, so just by looking at this key features here, you can already see that discharge summary would contain a very nuanced, fine-grained, granular information about the patient compared to what you dealt with so far, which are structured information. Structured information are just just numbers and codes and classes and labels. So they don't contain fine-grained like information like social family history. Like these are not in the tables. Like what kind of symptom the patient had, what kind of what kind of uncomfortableness the patient was experiencing, whether the patient was smoking, whether the patient has like genetic disease or something. Those are not usually stored in structured tables. These can only be found in text. So that is why a lot of doctors, a lot of biomedical researchers claim that like structured information would only if you only use structured information in your predictive model, you're only using like 30% of the patient information. Like 70% of the patient information actually are all stored in text. So that is why like they like to emphasize the importance or the vital information that is only stored in free text form. So you would, if you're interested in building better predictive model, you would have to somehow, like sooner or later, you would have to deal with patient free form text. So yeah, this is the typical content. So there's like, as I said, all of them have similar form, meaning that they have very similar number of sections. So there's like admission date, discharge date, gender, date of birth, service, allergies, attending, chief complaint, major surgical invasive procedure, illness, history, exam, lab results, and medications, discharge diagnosis, discharge conditions, follow-up instructions. Like these are like typical like discharge summaries. And based on how complex your condition was, or how much of a complex patient you were during your hospital stay, the length or the size of the discharge summary would vary. If you stayed only for like a couple of days, then this would be short. But if you stayed for like a month, then this will be like a long summary. So this is one of the actual example, and actually discharge summary is really heavily related to other tables. So like admission date and date of birth, discharge date. These are all information that you can actually find from admission table and patient table and services table. So patient table, admission table, those are where structured information is stored, but then those same information is stored in unstructured form in discharge summary, such as here, right here. And then physical exam and pertinent results are actually lab results. So all the lab related stuff can be found here, but they can also be found in structured table, which is lab events. But I'm not sure if I cannot guarantee that they would hold exactly same amount of information. Like lab events, and maybe lab events has more information, and like representative or like more important subset of lab events are recorded here, because this is a summary. This is discharge summary. And medications on admission, discharge medications there also can be found. They can also be found in the prescriptions table. Discharge conditions, discharge diagnosis, they can also be found in diagnosis table. But as I said, cannot guarantee they would be one-to-one. So maybe like discharge summary would contain a bit more granular information on subset of the information stored in the tables. So the best idea is to actually use both of them at the same time. Use both free text notes and structured table same time, using like multimodal approaches since they are actually, they're like complementary relationship between the two. So here, if you look at, I won't go. So like lab results can also be found in radiology notes. So this is an example like how different sections of discharge summary are linked to other structured table, and this is another view of the discharge note, how discharge summary is related to other categories of clinical notes, other clinical note categories, like such as physician notes or radiology notes. So because this is because discharge summary is a summary. It just summarizes everything that happened to the patient over the course of the hospital stay. So this is probably very natural that a lot of information from discharge summary is linked to other sources of information. Type 2 physician, so we'll just briefly go through them. Type 2 physician notes are physician notes, respiratory notes, and nutrition notes. So key features are physician note contain all table note information within 24 hours. So 24 hours, because as I said, physician notes are generated usually every 24 hours, or maybe like every 48 hours, based on how often the doctor checks up on you. So not all hospital admissions have physician note, because like if you're not very complex, if your condition is not very like severe, then the doctors might not actually say much about your status. So so physician note won't be generated for like simple cases. So so there are different subcategories of physician notes, like physician notes, intensivist notes, physician attending progress notes, resident notes. So like resident notes are actually generated by residents. 이제 레지던트, 인턴, 그다음에 전공, 교수님 이렇게 있잖아요. 그 병원에 가면 급이. 이제 누가 작성을 했냐에 따라서 이제 어텐딩 노트냐, 레지던트 노트냐, 이런 게 갈라집니다. So typically, this is the typical format that you see, like patient status, summary of labs and prescriptions, assessment. So the doctor would come to you and then assess your condition or status and then say something about that, and then they make a plan, like what to do with you based on the assessment. So this would be a typical physician note, and so you can just there are some overlapping information from other notes, like nursing notes, discharge summary, input-output events, lab events. Those are like overlapping information, and then these are assessment and plans. So you can read like 67. So this is written by the physician. So 67-year-old man with refractory IgA myeloma. So like this condition of the patient, yada yada yada, and then the plan is to do something like where is the plan? Yeah, here, like hold on. Is it abdominal X-ray? I'm not really sure what ABX is for now. Monitor urine CX. So these are like all abbreviations. One of the difficulties or challenges in handling clinical notes or actually any biomedical text is the abbreviations and the jargons and stuff. So you can see a lot of jargon like SXS, HCT, the ABX and CX. So is probably a good idea to actually have a dictionary for them. So anyway, yeah, monitor urine something. So these are like the plans, like 이제 그 소변 상태를 계속 모니터를 해라 이런 거겠죠. 네. Type 3 are nursing notes. So nursing notes are very often verbal expression of contents in chart events table. Chart events table is like what chart events is generated for patients staying in the ICU. So, and there's like a lot of vital information, vitality information, like 혈압, 온도, 체온, 호흡수, 맥박수 이런 것들이 계속 차트 이벤트 들어가니까 그런 것들이 주로 이제 너싱 노트에도 같이 이제 기록이 됩니다. So a lot of them are nursing progress notes, and then there's nursing transfer notes, which are I'm not sure what transfer notes is actually. I should not say something about it. All right. So most of them are progress notes. As I said, like every 8 hours, every 4 hours, or every 6 hours, nurses would check up on you. So even if like physician notes are sometimes not paired with the hospital admissions, nursing notes are always there. As I said, as you've seen, like there are at least like 1 million nursing notes in Mimic 3. Contents are not that different from the physician notes. It is a bit more oriented towards like what the nurses can do for the patients, like actions and responses, and assessment and plans are still there. So you can see that the assessment are like something related to that, and actions are the patient requires more morphine for the back pain. 이제 그 진통제를 놔줘야 된다 뭐 그런 거고, responses 했더니 액션 이제 한 거죠. 액션은 환자가 이제 몰핀을 놔달라고 했습니다. 그래서 뭐 놔줬더니 이제 그 진통 그러니까 이제 진통이 잘 컨트롤이 되고 있다. 리스폰스는 잘 컨트롤이 되고 있다. 그다음에 이제 플랜은 뭐를 이렇게 쭉 몰핀 이걸 잘 이제 팔로우를 해가지고 이제 너무 많은 양이 들어가지 않는지 이런 걸 해야 될 것 같다. 쭉 쓰는 그런 겁니다. 네. Right. So yeah, if you're interested in the progress, if you want to model the progress of the patient over the time while the patient is staying in the ICU, then you should actually be focusing on nursing notes, because there are a lot of them. And they, as I said, they capture fine-grained information like these, like actions and responses. They're nowhere to be found in structured tables. Like in the chart events, you won't find like actions or responses and plans. So if you want to know like details of the patient status, then nursing notes would be where you should go to. Yeah, I won't go into nursing others. Type 4 radiology, echo, and ECG reports. As these are just as written. So these are like reports from like images. So like imaging method, reason of imaging, why we're imaging this patient, like and findings and impressions, like what the radiology doctor found when looking at the X-rays, or what the impressions, like there is some nodule in the left lung, something like that. Like when you take an X-ray, there is a report always coming in. Like here, so I think this is a CHF. This is heart failure. So enlarge. I think this is I think this is chest X-ray. So like there's like impressions, enlarged cardiac silhouette. 이제 심장이 좀 커 보인다, 뭐 그런 거고. prominent lung volume, 뭐죠? 그러니까 폐의 그 사이즈도 뭐 커 보인다, 뭐 그런 거고. No acute process identified on single portable film. Not sure what this is. No acute process. 포털 실력이 뭔지 모르겠네. 뭐 이제 어떤 급성 뭔가가 이제 급성 뭔가 뭐 급성 무슨 뭐 폐렴이라던가 급성 뭐 그런 거 있잖아요. 급성 그런 것들이 뭐 있는 것 같진 않다. 뭐 이런 얘기인 것 같습니다. 네. So when you actually so in Mimic in the last project number 3, you could actually if you look at Mimic CXR dataset, which is another dataset, they are datasets of actual X-ray images in JPEG form or DICOM form. Let's say that they're in JPEG form. So JPG images along with this report. So you can actually like multimodal learning, that kind of stuff. So multimodal learning will be another topic we'll be covering this course. Right. Yeah, I'm going to the type 5 are just, as I said, supporting type of information. And if you're interested, you can look them up. All right. So, okay. So far, we just looked at a lot of medical text or clinical notes in Mimic 3. And as I said, if you're interested in medical, like biomedical, or actually clinical modeling or clinical research using AI, then you would definitely need to look at Mimic 3 chart note events. They're still not very intensely utilized, not as much as expected. They're usually used for like fine-tuning BERTs for BERT variants, but other than that, I haven't seen works that try to model patient progression in ICU using nursing notes, or maybe I just looked. I haven't looked hard enough, but yeah. All right. Well, yeah, we'll be looking onto text modeling now. So as I said, the first example would be model for performing automatic coding. So automatic coding is like a test, representative test that you can do with medical text. And so in order to explain automatic coding, I should remind you guys of claims data. So claims is a 청구 데이터네. 심평원 청구 데이터, 청구 데이터인데 이제 그 과정이죠. So this is a process. So the patient goes to the hospital, then after the discharge, the patient would only pay like small portion of the entire medical fee because the patient is insured. In Korea, the patient usually has 국민건강보험에 들어있죠. So there's a central insurance. So the patient would pay like maybe 10% of the total fee, and then the doctors would have to submit a report to the 심평원, to the government, what kind of service the physician has done on the patient. So there's like a specific form, and then based on the form, the 심평원 would review the form if it looks legit, and if it looks legit, then the 심평원 would pay the remaining 90% of the medical fee. So that is how claims data. So this would be claims data. So this is how the whole like reimbursement process, the claims process is done between the patient, between the doctors or the hospital and the government. So this needs to be generated somehow. So this here. So this is claims data. So it contains provider information, basically, of course, the hospital information, the medical license, and then the patient information, because every patient has like 주민등록번호. So and 주민등록번호 is how the government recognizes which insurance plan the patient is in. And then the diagnosis code, treatment codes, like a lot of different, basically these are the services, right? These are the services. And then the billing information, like, that's patient specific. So this information needs to be recorded or generated by the hospital or by the physician, and then this should be submitted to the 심평원, so that the 심평원 can look them up, take a look at it, read them, and then see if it looks legit. 그러니까 이제 의료보험 사기 뭐 이런 것도 많이 칠 수 있으니까 뭐 하지도 않았는데 했다고 막 여기 써놓고 그럼 이제 뭐 비싼 약 처방했다고 써놓고 뭐 비싼 수술했다고 써놓고 그럼 이제 돈 많이 받고 뭐 그럴 수도 있으니까 이제 그런 거를 심평원에서 이제 다 리뷰를 해야 되잖아요. 그래서 요거를 잘 써야 되는데, 그러니까 이거를 so in the perspective of the hospital needs to write as detailed as possible so that they don't lose out on the money they should receive, because they've only received 10% of the fee from the patient. So they would like to receive the remaining all 90% of the fee from the government. So they need to write as detailed as possible. So they don't lose out on the money. 그러니까 이제 손해를 보면 안 되잖아요. 최대한 한 거 다 받아야 되잖아요. 근데 또 너무 많이 막 쓰면은, 과하게 쓰면은 이제 그 심평원 입장에서는 아 요건 이상하니까 너는 요거는 제하고 내 요거만 해서 줄게. 뭐 그러면 이제 뭐 원래 90%다 받아야 되는데 80%밖에 못 받는다던가 뭐 이런 일이 있을 수 있기 때문에 이 병원 입장에서는 요거를 잘 쓰는 게 아주 중요해요. 이 돈을 잘 받는 게. 이게 그리고 이제 심평원뿐만 아니라 실제 보험사한테도 마찬가지죠. 개인 보험을 들은 사람들이면은 뭐 무슨 실비보험이니 뭐 실비보험 사람이 내는구나. 그러니까 뭐 무슨 개인 보험 하여튼 뭐 암보험이나 뭐 이런 거 들었으면은 이런 걸 잘 써가지고 내야지 이제 보험사에서 또 돈을 주니까 이제 그런 것들이 이걸 잘 쓰는 게 이제 굉장히 중요합니다. 이제 과하게 써도 안 되고 덜 써도 안 되고 딱 필요한 만큼만 써서 딱 필요한 양의 돈을 받아내야 되는 게 이제 병원의 입장입니다. 병원뿐만 아니라 동네 병원도 다 똑같은 그 프로세스를 거치게 됩니다. Alright. So as I said, like writing a very detailed, very proper, like legitimate discharge. No, the claims form is very important for hospital for the financial purposes. So, and usually the hospitals or the physicians can write this claims data is based on the discharge summary. So these days, I don't know, some EHR solutions, EHR software would require like the physicians or caretakers or the providers to enter information to the claims form as they treat patients. Maybe that is, I'm not sure, like I'm not a doctor, so I don't know, but one of the ways that these claims data or claims form is filled is based by reading discharge notes or some kind of summary written by doctors. So some other person would read the reports or the summaries written by the patient, written by the doctor, and then they would fill in the blanks. 그러니까 이제 이 의사 선생님이 쓰신 요 서머리나 소견서나 이런 거를 보고서 이제 밑에 있는 누군가가 뭐 의대생일 수도 있고 뭐 레지던트일 수도 있고 아니면 알바일 수도 있고 누군가가 이걸 읽으면서 이제 요런 일들이 일어났으니까 이제 진단 코드는 뭐를 쓰고 요 폼에다가 이 보고서에다 진단 코드는 뭐 쓰고 뭐 약품 코드는 뭐를 쓰고 이 시술 코드는 뭐를 쓰고 이제 코드를 뭘 써야 될지를 정하는 거예요. 사람이 이걸 읽으면서. 굉장히 이제 아주 그 노동력이 많이 필요한 일이죠. 그러니까 의사 선생님이 쓰신 걸 보고 누군가가 요러한 서비스를 했으니까 이제 요러한 코드를 쭉 쓰면은 대충 어떤 뭐 몇 프로의 돈을 받아낼 수 있겠구나 이런 감이 있는 사람이 이걸 주워 읽고 그걸 쓰는 거예요. 이제 앉아가지고 굉장히 아주 그 레이버 인텐시브한 아주 그 진한 이 고통스러운 일이 되겠죠. 그래서 이제 그거를 자동화하는 일이 바로 오토매틱 코딩입니다. 그러니까 이제 병원 입장에서는 그 인력과 인건비도 줄일 수 있고 이게 만약 굉장히 정확한 정확도로 이제 이게 이 폼이 채워지면은 이 보험 뭐죠? 이제 그 의료 수가도 보험 뭐죠? 의료비도 많이 받아낼 수 있고 참 많이는 아니지만 정확하게 받아낼 수 있고 이제 아주 그 병원이 눈독을 들이는 태스크 중 하나예요. 그리고 이제 사람이 하면 실수를 할 수 있잖아요. 이제 뭐 코드를 잘못 적었다든가 아니면 코드를 빼먹고 적었다든가 뭐 이런 일이 있을 수 있기 때문에 그런 병원 입장에서 손해가 나기 때문에 이제 이거를 자동화하는 그 일에 굉장히 관심이 많습니다. 병원들은. 네. 그래서 이제 오토매틱 코딩이라는 태스크가 이제 거의 뭐 이게 별로 어려운 태스크가 아님에도 불구하고 이제 그 계속해서 뭐 머신러닝 학회나 무슨 뭐 헬스케어 학회 같은데 이제 자주 등장하는 단골 그거입니다. Alright, so this is the story behind the automatic coding. So the first neural network, as far as I know, I don't know all the papers in the world. So as far as I know, the first neural network paper that tried to do this automatic coding was this paper, Explainable Prediction of Medical Codes from Clinical Text, which was 2018 NACL paper. So this is not that long time ago, actually. And so this is performing automatic coding. So based on 50,000 discharge summaries from Mimic 3, so Mimic 3, 50,000 discharge summaries, they try to classify that free text note into 9,000 codes. So 7,000 of them are diagnosis codes and 2,000 of them are procedure codes. So as I said, IC9 codes are developed or they were devised for billing purposes. 그러니까 IC9 코드는 애초에 이걸 하려고 나온 거예요. 이 청구를 하려고 만들어진 체계입니다. 그러니까 사람을 치료하려고 이제 치료를 어떻게 하면 제일 잘하나 그걸 생각해서 만든 코드 체계가 아니라 어떻게 하면은 이 정부한테서 이제 돈을 잘 받아낼 수 있을까? 내가 이제 병원에서 무슨 일을 했다라는 걸 잘 받아내기 위한 체계예요. ICD-9, ICD-10, ICD-8 뭐 다 뭐 쭉 이러니까 그런 체계이기 때문에 요거를 이제 이 디스찰지 서머리 보고 요 코드를 맞추는 게 사실상 오토매틱 코딩의 정수입니다. 네. So as written here, so you put a this single discharge summary into a one-dimensional ConvNet, and then the output will be 9,000 way softmax classifier. Actually, it wouldn't be softmax because it's a multi-label setting. So the patient obviously could have received like multiple diagnoses because of multiple procedure codes. So this would actually be a multi-label classification rather than multi-class classification. So the architecture itself is pretty straightforward. If you guys are already all familiar with hopefully you guys are all familiar with 2D convolutional neural networks. So this is just a one-dimensional adaptation of that. There's a question. 그럼 diagnosis, so question from 최진아님. diagnosis ICD 코드는 주어진 서머리에 대해 이상적인 코드라고 생각하면 되는 건가요? 적어도 청구용으로는 이상적인 코드라고 볼 수 있겠죠. 그러니까 이제 환자의 질병을 나타내는데 가장 이상적이진 않아요. 절대로. 왜냐면 애초에 이 ICD-9 코드를 만든 이유는 돈을 받기 위해서 만든 거지 환자의 상태를 나타내기 위해서 만들어낸 게 아니에요. 그렇기 때문에 뭐 어떤 의미에 가장 이상적이냐? 돈을 받아내는데 가장 이상적이라고 볼 수 있겠네요. 이제 병원 입장에서는 내가 이 환자에게 한 행위 중에서 진단 행위가 있을 거 아니에요. 진단. 그러니까 이제 수술, 진단, 처방이 다 다른 행위잖아요. 그러니까 이제 진단 행위에 대해서 돈을 받아야 되는데 그 돈을 받을 때 진단 행위를 나타내려면 코드가 있어야 되잖아요. 체계가 이제 뭐 그래서 만든 게 ICD-9이고 그래서 이제 401.9면은 이센셜 그러니까 뭐죠? 고혈압이잖아요. 근데 고혈압에 대한 진단은 뭐 얼마, 뭐 10,000원, 뭐 그런 겁니다. 그러니까 이제 돈을 받아내기 위한 체계. 그래서 뭐 가장 청구를 위해서 이상적인 체계라고 보시면 되겠습니다. 네, 현지님, 현실에서도 병원에 오토매틱 코딩이 적용되어 있나요? 좋은 질문인데 잘 모르겠네요. 아마 시범적으로 사람이랑 같이 뭐 병렬적으로 하는 데가 있지 않을까요? 어쨌든 간에. 아니면은 뭐 초벌로 이제 1라운드로 일단 오토매틱 코딩을 하고 2라운드로 사람이 보고 뭐 이런 데가 있을 수도 있겠지만 아마도 아직까지는 풀리 오토매틱 코딩만 하는 병원은 없을 거예요. 이게 뭐 아직 뭐 이렇게 뭐 머신러닝이 뭐 슈퍼 릴라이어블한 뭐 그런 게 아직 아니기 때문에 아마 병렬적으로 하거나 아니면 초벌구이로 하고 이제 재벌로 그 사람이 하거나 뭐 그렇게 하지 않을까 싶습니다. 네. 하지만 굉장히 관심이 많은 아주 왜냐면은 이거를 하는 인력이 따로 있기 때문에 병원들이 그 사람들을 자르고 싶잖아요. 병원 입장에서는 인건비를 절약하기 위해서 그렇기 때문에 이제 오토매틱 코딩에 관심이 있는 겁니다. All right, so as I said, the architecture is pretty simple enough. It's a one-dimensional adaptation of two-dimensional ConvNet. You can just, even if you're not familiar with one-dimensional ConvNet, hopefully this diagram would actually make it familiar for you. So right here, so yeah, you just have a sequence of tokens. In this case, it's just a sequence of words, but this could easily be subwords. But back in 2018, when this paper was coming out, it was the subwords were not that much, was not heavily used back then, or at least in this case. So this is just word-based sequence. So it's a sequence of words, and you can for example, let's start. The starting sentence is, this is an 81-year-old female with knee pain and yada yada yada. So this would be like a very long text. So typically, as I said, discharge summary can be really long. So in this case, in this paper, they actually they thresholded the maximum length of the words as, I think they use like 1,000 or 15, like 1,500 words or something. So it's still a pretty long sequence of words. Anyway, so one-dimensional ConvNet. So one-dimensional ConvNet, you can think of them as like similar to it's just you have a filter. Just like a 3x3 filter used for images, you have a 1x3 filter because this is a one-dimensional sequence. So there's one 1x3 filter that just goes through all the sequence of words, and that's it. So if you remember how two-dimensional filter is used for images, so in images, the input image would be, for example, like 128 by 128 by 3. The last 3 will be like color channel, RGB. So in this case, this would be width, so like width or the filter size. So as I said, this is a 1 by 3 filter, so it would only cover 3 words at a time, three words at a time. There is no height, there is only width because this is one dimensional. So this width equals 3, and depth is the channel size. So input channel, instead of RGB, this is a word embedding. So you can think of them as like a word embedding trained on Word2Vec or trained by glove. Like, this could be like 128 dimension. This could be a 128 dimensional word vector. So instead of three dimensional input, like instead of RGB, this is just 128 dimensional input. So this would be depth. And then if you have a single filter, if you have one filter, then there will be one scalar output for these 3 words. So, but if you have multiple filters, like typically in ConvNet, you have like 64 filters or 128 filters or 256 filters. So that number of filter determines the output size. So the output size here is determined by the number of filters. So if this is 128 again, then it means that you're using 128 filters, where each filter has each filter is 1 by 3 size with depth 128. Right, so that is one-dimensional adaptation of two-dimensional of ConvNet. So hopefully this is all really clear. No question here, right? So no question here. And then once you figure this out, then you just slide them over the words. So slide them like this, and then you just keep on going until the end of the sequence, and then you would have H1, H3, H4, H5, H6. Like, like there you would exactly have if there were 100 words, then you would have 98 H's. Or if you just pad them, like if you have one additional pads at both ends, then you would have exactly 100 H's. In this case, there is no padding here, but it's up to you. So this is, so once you have actually you just went through all the, if you just slided your filter throughout the entire sequence, you would have 90, you would have like these H's, and you could actually do them again. You can actually stack them with another ConvNet layer. So you would have like, another layer of H's, and then you can do this like not a lot of stacks basically. But here in this paper, they only use one layer of ConvNet. That's it. They just use one layer of ConvNet. So with H1A, so you would have a lot of H's, and somehow you need to aggregate them into a single fixed size vector so that you can push them into multi-label classifier. So you need an aggregation function, and what they use for aggregation is, I mean, you could obviously just do max pooling over the entire H's. You can just max pool them, or you can average pool them, you can sum them, or whatever you want, you can do them. But in this paper, what they did is they just did the attention pool. So they're just another attention function that determines the alpha weights, and then they just sum them with all the H's to get a V. So this is the aggregate fixed size vector for diagnosis 1. So they have attention per label. So there are 9,000 labels, like 7,000 diagnoses and 2,000 procedure codes. So there are 9,000 labels. So for each label, they have individual attention functions. So there's attention function for diagnosis code 1, attention function for diagnosis code 2, so they would have like 9,000 attention functions and 9,000 aggregate fixed size vectors. So you just push each of them into a logistic regression, basically a sigmoid classifier, to generate to simply classify 0, 0, 1. So this is used for predicting whether there should be a diagnosis 1 or not. This fixed size vector is used for predicting whether there is diagnosis code 2 or not, 3 or not, all the way to different 9,000 codes. So basically, this is it. So it's not that much difficult. So hopefully this is super clear. You can easily do this with actually RNN as well. You can just feed these code, these word sequences into RNN, and then just simply use the last hidden layer to do this kind of prediction. But they just chose to use ConvNet layer. I don't know why. But this actually performs really well. So compared to other other baselines. So simply using just ConvNet, and then So this would be ConvNet without the attention function. This would be GRU, bidirectional GRU without the attention function. This is their model, and this DR camel is actually their variant of the camel, their model, using code descriptions, like like ICD-9 4010.9 is unspecified essential hypertension. So they would use that free text code description somehow to embed them into the model. But this is just another additional technique. So you can just focus on camel itself, which is just one-dimensional ConvNet with attention aggregation, and you can see that it performs really well. So here, diagnosis code for diagnosis code. It shows about 52% F1 score. For procedure codes, it shows about 60% F1 score. And for procedure, precision at 8, precision at 15, you can look at them. Basically, micro AUC is really, really good. So as far as like really frequent codes go, frequent diagnosis and procedures go, the camel model can be really, really accurate. So, right. And yeah, I mean, there is still like some room for improvement in this area, F1 scores and precision and recall. So there are some follow-up works that tries to do automatic coding with better models, like probably with BERTs or that kind of stuff. So better model, and try to outperform camel, which they actually do. So if you're interested in them, then you can look them up. And since they actually use attention function, they actually show a bit of qualitative example for model interpretation using the attention. So so here these are different baselines. So camel is their model. Actually, no, let's start with this. So the model, there are different models like camel, cosine similarity based models, ConvNet model, logistic regression model. There are different automatic models for automatic coding. And this is the case where all the models predicted 934.1, which is foreign body in main bronchus. So this is like one of the ICD-9 diagnosis codes. And using different models have different ways to interpret them. For example, logistic regression, you can just simply look up the coefficients, like the most prominent coefficients for which ones are the most important features. And camel, you can simply look up the attention values. So, and then they gave these examples to an actual physician to read the most prominent, which is bold type here, the most prominent sections of the text, and then annotate whether they're highly informative or just informative. So there's an actual doctor who went through some examples, and so in this case, the doctor went through 1, 2, 3, 4 examples, and 1 out of 4 examples, this one showed the most highly informative evidence for this predicting this code, which is true, which is actually the case, because foreign body main bronchus, 그러니까 이 뭐죠? 그 브론커스는 뭐야? 폐꽈리인가? 폐포인가? 하여튼 뭐 폐 어딘가에 어떤 이물질이 들어왔다 이건데, 이 볼드체들 보면은 나머지는 다 그냥 뭐 별로 그 의미가 없는데, 얘만 이제 large mucus plug이니까 이제 그 어떤 가래가 꼈다 뭐 이런 얘기거든요. 이제 얘만, 이 캐멀만 이제 그걸 잘 포착을 한 거죠. 그래서 얘가 이제 highly informative다 해서 여기가 된 거고, 뭐 이런 경우는 이제 aneurysm of other visceral artery, 이건 뭐예요? 이건 뭐 동맥에 뭐가 꼈다 뭐 이런, 뭐 aneurysm 뭐 꽈리가 꼈다 뭐 이런 거 같은데, 하여튼 그걸 보면은 이제 여기서는 2개가 또 prominent하다. logistic regression은 hepatic artery branch pseudo aneurysm 뭐 비슷한 얘기죠. 그러니까 아마 얘도 그렇고 2개가, 그래서 2개를 이제 informative를 준 것 같고, 뭐 얘는 이제 여기서는 systolic heart failure니까 뭐 이거는 뭐 신부전인데, 그나마 여기서는 캐머리는 딴 애들 잘 못했는데 얘가 제일 잘했다. 그래서 뭐 디스펑션, 이제 말펑션, 그 펑션을 잘 안 한다 뭐 이런 거니까 뭐 제일 잘한 거겠죠. 그래서 뭐 어쨌든 뭐 그렇긴 한데, 통계적으로는 이제 so statistically camel actually showed the most highly informative compared to other baselines. So you can, but code description is basically using the code description. So this is actually using ground truth compared to other models like logistic and CNN. Camel actually showed like the best performance for interpretability as well. So it's that is their claim. So anyway, so that is the model camel for automatic coding. And what you're going to do is automatic coding for project number 2 if you decide not to do your own projects. So hopefully this is this draws a clear picture for everybody. All right, so we'll only have maybe 10 minutes. So I'll just, actually, we don't have a lot of slides to go through. There's only like a couple of them. So this section, so the last section is actually, I was hopefully trying to introduce BERT variants for biomedical domain only. Well, not only, but for BERTs developed for biomedical domain or biomedical purposes. And actually, I was going to go through some basic, preliminary stuff for how to train BERT. But hopefully, everybody actually knows BERT, right? So, like everybody understands BERT, hopefully. So I'm not going to go through them. So yeah, this is just the architecture of the BERT, and then how you do mass language modeling, and then close tag, and how you do next sentence prediction, and then the BERT actually showed like great performance of SQUAD dataset, which is Q&A dataset. Maybe some of you guys don't know what SQUAD dataset is. So it's a Stanford question answering dataset. It's just like 수능 언어 영역이랑 똑같습니다. So there is a text, reference text, and then there's a question. And then the model needs to answer the question, where the answer is actually in the question. So it's a highlighting task for the model. So given a reference text and a question, the model needs to highlight a specific span in the reference text. So the human performance is about 90% or 90% F1 score, but already BERT-based models outperform humans, like 93%, 93%, 93%, 93%. All the way to like 92%, right? So it's already like that is like showing the power of BERT. And because of this, people try to develop BERT for biomedical tasks. So what they did is actually I forgot to mention this: how to fine-tune BERT for SQUAD. So BERT is trained with these two tasks: mask language modeling and next sentence prediction. How to fine-tune them for a specific task. In this example for SQUAD is like this. So there's a question, there's a reference text, and then you put those two texts into the BERT input. So there's like question part, and then there's a reference part. And all you need to do to fine-tune BERT for SQUAD is to find the starting span and the ending span, because what you need to do is just simply highlight a span of text in the reference text. So the question is, how many parameters does BERT have? And the answer is here, 340 million, which is 300. There should be like blank here and then million blank parameters. So you need to train your model. So the BERT. So this is the reference text, or like a piece of the reference text, and there's 340 million params total. So the start of the span should be here, and then the end of the span should be here. So that is how you fine-tune your BERT. And then if you actually do it, then this is the actual logit values. So this is not the probability value. This is the logit value. Here is the span of questions, and then here's the span of reference text. And of course, obviously the start should be here. So this is prediction of start span. So 340. It has the largest logit value, and then interestingly, in the ending span has a bit more varied flavor. So here's the highest logit value is here in M, but it could equally be here, which is parameters. So the answer to the question, how many parameters does BERT large have? The question could easily be 300 million parameters instead of 300 million, because that is also a very valid answer. So that is why there's like the second largest logit here. And obviously, syntactically speaking, 340 can also be at least syntactically, grammatically correct answer. So that is why 340 has a large logit value here as well. So that is like the introduction to the BERT. So now we'll move on to BERTs for biomedical purposes, and the most well-known variants of biomedical BERT is called BioBERT. This is actually, so the name of the BioBERT is pre-trained biomedical language representation model for biomedical text mining. So this is actually from Professor 강재욱 교수님, 고대에 계신 강재욱 교수님 랩에서 만든 버트입니다. 그래서 굉장히 이제 처음으로 했기 때문에 아주 많은 주목을 받았죠. So what they did is they just took BERT base, I think it's BERT-based. Yeah, I think so. They took BERT-based so initialized their BERT with BERT-based parameters, and then they further additionally trained the BERT-based with PubMed and PMC article, where there are 4.5 billion tokens and 13.5 billion tokens. They basically did the same thing. They just did mask language modeling and next sentence prediction on top of BERT weights. So it's like fine-tuning BERT for these corpora. And they took 23 days on 8 NVIDIA V100 GPUs. So that is a lot of effort, a lot of electricity bills. So once they have BioBERT pre-trained for once they have BERT pre-trained for biomedical text, like biomedical corpora, they use that BioBERT for these specific tasks, which are named entity recognition for biomedical text. So 이제 그래서 뭐 논문을 쭉 읽으면은 뭐 아까 말씀드렸듯이 뭐 structured information extraction 한다 그랬잖아요. 이제 논문을 쭉 그 biomedical abstract 읽으면서 뭐 이 유전자가 뭐 저 유전자를 뭐 같이 발현된다. 뭐 이 단백질 저 유전자를 뭐 그 인히빗 한다 이럴 때 그러면 유전자랑 단백질의 이름을 파악을 해야 되잖아요. 그 정보를 정보 추출하려면은 이 엔티티의 이름들부터 파악을 해야 되거든요. 그게 바로 named entity recognition입니다. NER, 개체명 인식이에요. 개체명을 인식해야지 그 다음에 그 개체랑 다른 개체가 무슨 관계에 있는지 관계 추출을 할 수가 있거든요. 그 관계 추출이 바로 relation extraction입니다. 그래서 개체명 인식하고 관계를 추출한 다음에 그 다음에 이제 뭐 어떤 온톨로지나 뭐 널리지 베이스나 널리지 그래프를 구축을 한 다음에 거기서 이제 question answering을 하는 거예요. 아니 뭐 이제 추론을 한다던가 inference 한다던가 뭐 그런 겁니다. So yeah, so these are all NLP specific tasks that is oriented towards biomedical text. So like named entity recognition, relation extraction, question answering, these are all like NLP fields, but in this case, there are subdomains of NLP where it's called biomedical NLP, and these are like all fine-tuned for biomedical purposes. So there are a lot of open source data sets for biomedical NER, biomedical relation extraction, biomedical QA, and you can fine-tune BERTs, fine-tune BioBERTs for all these tasks. Like for if it's biomedical QA, you can fine-tune BioBERT exactly like you would fine-tune BERT for squad data set, right? So there are a lot of BERT variants for biomedical domain. After the introduction of BioBERT, there's like clinical BERT, there's bioclinical BERT, there's blue BERT, there's PubMed BERTs. I'm pretty sure there are like at least at least dozens of BERTs that is fine-tuned for biomedical purposes. So the difference between them are some are fine-tuned on PubMed abstract, PubMed central, such as biomedical, BioBERT. Some are fine-tuned. Fine-tuned meaning like they take BERT base and then further tune on PubMed abstracts and PubMed central. Some are fine-tuned on mimic-free notes, like clinical notes, like discharge summaries, physician's notes, nursing notes. They would take those note events text and then fine-tune BERTs on top of them. Some are fine-tuned on both PubMed centrals and PubMed abstracts and mimic-free notes. So there are different variants. Some use BERT original vocab. Some use customized vocab. So like again, like different variants. And many of them are available on GitHub or like based on author GitHub or Hugging Face. So you can take them as off the shelf and then use them for your own purposes. So if you're interested in biomedical NLP tasks like these, you can hopefully use them for that task. Actually, you can use these even for automatic coding as well. So you can just fine tune whatever BioBERT or BlueBERT, PubMed BERT, whatever you take. Any of these BERTs from the GitHub or Hugging Face, and then you would fine tune that BERT, that biomedical purpose BERT on automatic coding test itself, and then you would have a very powerful automatic coder. You can easily do that for your project number 2. Right, yeah. Okay, so this is the end of the class today. So we only actually, yeah, I expected to end this early, but this took longer than expected. So, all right, so. Any questions so far? Thursday, we'll be talking about the specs of project number 2, so you don't need to worry about that today. All right, if there are no more questions, this is the end of the class today. I'll see you guys this Thursday. Bye-bye.